5.4. You can solve problems about rigid bodies resting in limiting equilibrium. Okay, in other words, it's going to topple or fall. It's just on the point of moving. It's most extreme. So when a body is resting in equilibrium and one of the forces acting on the body is a frictional force, you need to consider whether the body is on the point of moving. Now, you can do one of two things. If it's on an inclined plane, for instance, which is a lovely typical question, it can either slide down the rough inclined plane or it could topple. Now, we've got to be able to work out which one is it doing first. Will it exceed as the centre of gravity, as the inclination goes up, the centre of gravity slips beyond that corner, the toppling corner, before the friction is max is achieved? One or the other, and we've got to work it out, okay? So if a body is on the point of moving, then it is said to be in limiting equilibrium. In this case, the frictional force takes its maximum value, i.e. mu r, where mu is the coefficient of friction and r is the normal reaction. You should know that. Okay, so example 5. A uniform rod AB of mass 40 kilograms and length 10 meters rests with one end on a rough horizontal ground. The rod rests against a smooth peg, C, where AC is 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees horizontal. Right, we've got a diagram. Change of pen, the pen looks like that, black, and we've got a ground. Okay, ding, 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 ding. You've got the rod, okay, uniform rod, and its peg is 8 meters, so it's just a little circle, as it were, there. And does it say smooth peg? Yes, it says smooth peg, i.e. there's no friction. Now, how do you get friction on a smooth peg? Well, if it's a rough peg, it acts along the tangent to it, which is the rod itself. If it was rough, it's not, so we don't have to worry about it. That distance there is 8. From here to here is 8, leaving this distance from here to here as 2. It's a uniform rod, so right in the middle here is your 40 kilograms, which is 40 G, and the angle of inclination is 15 degrees. Okay, and it's in limiting equilibrium. Now the ground is rough again, rough horizontal ground. So what you'll have here, if I just change my colour, is you're going to have a reactional force provided by the contact surface, which is always perpendicular, so it's going to go straight the way up. You're going to want to stop the sliding of this going down, and the friction is doing that, and that's going to cross like that. And because we're told it's in limiting equilibrium, we know that this is actually F max. So if you see those words, you can instantly assume that. Now, does it mean it's moving? No, it hasn't exceeded. It's just got there and is on the point of moving. So it's just got there. This is a reactional force going upwards. Okay, so I'm going to call it R1. And the other force we've got to worry about is the normal to this little peg, which is the contact is doing that. That's R2. Okay, and there's nothing else there on the diagram I've got to worry about. So, changing that. Okay. Again, it says find the magnitude of the reaction at C. So I want to find this here. Okay, the reaction at C. Right, so I better label that as C, and I suppose that is A, and that is B, the end of the rod. Now, where would you want to take moments? Well, I want to take moments about A, because I can negate R1 and F max. I can get rid of that if I take moments there. So that's the technique for doing these kind of questions. So at A, we're going to take moments. I suppose you could have said that straight off as a moments positive clockwise, I'm going to say. Okay. Right. So what I've got is my only clockwise one is what? Well, it's the weight component. And remember, it's going to be perpendicular. So I could look at finding this length here and doing that force, or I could componentalize it. Now I just love componentalizing it. It just makes more sense to me. The other component is going through the fulcrum and it's going to have no effect. So it's only that bit I've got to worry about. That's 15 degrees. So the force itself is the clockwise force itself is 40g cos 15, but don't forget to times it by its perpendicular distance. Now this is a uniform rod, so it's halfway between the 10 meters that exists, so it's 5. So I'm going to multiply that by 5. That's the first moment. Now my mistake when I'm doing these is I forget to times by the perpendicular forces. That's a mistake. Now the other force is a minus, so it's the other moment is a negative, because it's going anti-clockwise, and that is R2, which is what we're after, and we're multiplying that by its perpendicular distance, which is 8. Now it's in limiting equilibrium, but it's still in equilibrium. It's still balanced. It is the sum of the moments is equal to 0. So therefore, to work this out, R2, which is what we're after, is simply equal to 40g cos 15. In fact, I'll do the 40 times by 5 to give you 200, and divide it by 8. And yeah, the 8 could have gone into there quite easily, but it's too late now. Work that out, and what do we get? No, well, as an answer, anyone? We've used G, so it can only go to P6 Pig. 237. 237 newtons is the normal reaction. Okay, at C. Now we've got to find the coefficient of friction between the rod and the ground. So to be able to find that this friction here, this friction max, is to do obviously with its contact of the surface. It's nothing to do with this, it's to do with this contact. So R1 is what we need to find, and mu R is then what we need to find from there. So we've got this. Now I'm just going to resolve vertically, because I've got that, and I know that, so I'm away. So there's a number of ways you can do it. You can take moments and things like that to get simultaneous equations. But I think the easiest way on this one is to take resolving vertically. Okay, so I've got that. So straight off, R1 is positive, plus the component of this going upwards is going to be R2, and it's going to be cos, because if it's 15 degrees there, you think about it, it's 15 there, that's 90, take 15, and that's going to be 15, obviously. Do one, miss one, do one, miss one, etc. So that's 15. Okay, so it is going to be the force R2 cos 15, it's in the pinch, is the vertical component. The horizontal one is at 90 degrees, so it has no effect, obviously. And the only other thing is the weight. So it's take away 40g. The sum of those forces must equal 0. Mass times acceleration, there's no acceleration. So R1 is equal to 40g minus whatever R2 is, and the unrounded R2, times by cos 15. Okay, so we get... Anyone's done that? Anybody prepared to say apart from a T, because T can give me the first answer, can someone verify it? We get? No, good problems. Anyone else get 163? Yeah, you did? Okay, 163 it is. So 163 newtons. Right, and you said here the coefficient of friction between the rod and the ground. Okay, well, I'm now going to work out F max. F max is going this direction, so I'm now going to resolve in the direction of F max, because that's what I need to find. So F max, because it's in equilibrium. I've got F max is the only positive force, minus the only component going in that direction, okay, because that's acting vertically downwards, is this bit here, which is skew, so that I'm going to do that bit just there, which is going to be the force R2, and it is sin of 15 degrees, okay, and that's it. I've got my vertical force there, I'm not worried about anything else, so 1 is equal to the other. So that is equal to 0, and straight off, F max is equal to whatever R2 is again, times by sin 15, and we get a nice unrounded answer on that one. 61. The weight, if you're looking at it, so let's forget that just there. Okay, the weight, yeah, the weight's just acting vertically downwards. Okay, so 60. Did someone verify that? 63 newtons. 61 newtons. Okay, and finally, the last formula you're going to use is F max is actually equal to mu r. So mu is simply F max divided by r. So what we're going to do is 61 unrounded divided by 163 unrounded. Anyone verify what we're going to get? 360. 0 point something. 38. Usually vigorous one more. 376. Okay, there's no units to it, it's just a number. Okay, and that's what we make it. 0.376. Okay, so as long as you're not, I've seen people leave answers such as 10.7 from mu. Mu, you know, lies between 0 and 1. It should ring alarm bells. I saw someone in the exam, David Baird, last year, panicked because he knew that it was wrong. He knew that the centre of mass was acting on a rod, I don't know, something like a 10-metre rod. It was acting at 20 metres over here, which is impossible. So he obviously, you know, he was aware he was wrong, so he had to go back and check. He found where he was wrong and corrected it. But if you're not aware of what you're expecting, then that's where problems happen. Rob? How do you decide that? What does that mean? Yeah, the ground was rough, the peg wasn't rough. So it's on the ground. Okay, so we've got over the page, example 6. Okay, right, a ladder AB of mass M. It hasn't said it's uniform yet, so we can't assume it's uniform. So a ladder AB of mass M and length 3A has one end A resting on a rough horizontal ground. Well, as soon as it says rough, I'm going to say that that's going to want to slide down, and that's going to slide away. So stopping that sliding away is the friction. Now, again, we know this is talking about limiting equilibrium. I can see the words there, limiting equilibrium. So that, therefore, can be now written as F max in that direction. To work that out, I'm going to need the contact reactional force, which is a vertical, so perpendicular to the contact surface, which I'm going to call, I really don't like R1s and all that. I'm going to call that just A, capital A. Okay? Yeah, but that's just a point in it. Oh, I don't know, you always make things hard for me. I'm going to call that a Y. There, how about that? Okay? Right. The other end, A rests on rough, the other end, B rests on a smooth. So all this has got is no friction, so there's no vertical up or down. You've just got the contact surface providing a normal reaction. And I'm going to call that X. Okay? Right. The other end, B. A load of mass 2m is fixed at ladder point C, where AC is A. So that's A. So I've got a mass of 2mg. Sorry, the weight of 2mg. Ladder's models are uniform rods. So I've seen the word uniform now, so it's acting right in the centre. So going down there, the mass of that was m, so it is now mg. And that's it. The angle's 60 degrees. It's in limiting equilibrium. As soon as you see those words, you know that this is at F max. Find the coefficient of friction between the ladder and the ground. Right. So it's a very similar question. Now, the trouble is, if I take moments around here, point A, this is known, and it'll find this straight off. So I'm going to do that actually, so I can find this straight off, and then I can find F max because that's the only horizontal, and it will be equal this, and then I'm going to resolve vertically to get that. So it's a straightforward question. Okay, so we need to work out y. Remember, it's not x. We ultimately, to find mu, need the r, which we've labelled as y, and the F max. Okay, of that contact surface. And then you divide the F max by the y and you get the mu. So here we go. We're now going to take moments. So take moments. Clockwise I'm saying is positive about A, and I'm choosing A so it negates y and F max in one foul swoop. I'm going to componentalize these forces. Okay, but I'm not going to mess my diagram up. The only clockwise two are the weight and the mass that's been put on there. So I'm going to do the 2mg first of all. Now this is where I frequently forget, I have to remind myself to times it by the perpendicular distance. So the component is 2mg and it is cos 60, and times by its perpendicular distance is a. There's the first one. The next one is a positive because it's also clockwise. It is the component is mg cos 60 again, multiplied by its perpendicular distance because it's uniform and it's a 3a. It's going to be 3a over 2. 3a over 2. And the x, the reactional force at B, is your negative because it's going anti-clockwise. So minus. Now the component, you can either bring this across and work out the height here using trig. That'd be quite straightforward. I'll go straight off to componentalising it. That bit there. Okay, this is 60 just here, that's 60 just there, therefore that's, if I'm going to label that as 60, just there, because of the alternate angle law, 60, that means that this is now not in the pinch. So that is the force X, it is sin of 60, but don't forget to times by the perpendicular distance, which is now 3a. And you'd have got exactly the same answer if you worked out the height of here. It is 3a sin of that 60, because 60 is up here. Okay, it's the opposite. Okay, so no matter how you look at it, there's two ways. I like to componentalize. Equals 0 because it's in equilibrium, limiting equilibrium, but it's still in equilibrium. Cos 60 is half, so I've got basically mga here. I've got a half, so I'm going to write that out. mga plus, and I've got a half again, so that's going to be 3mga over 4 minus, that's root 3 over 2, so I've got 3a root 3x all over 2 is equal to 0. Okay, I'm going to throw that over, work this out, and times by 4. So I end up with 4mga plus 3mga gives me 7mga is equal to, times this by 4 leaves me with 2 on top, gives me 6a root 3x. Divide by that and you get, cancel the a's, and you end up with x is basically 7mg over 6 root 3. And you would leave it like that because we don't know what m is. Okay, so that's what x is. Now, as you can see, we're going to resolve horizontally now. I'm just going to rub that out because it's messed my diagram up. We're going to resolve horizontally, and I'm going to say the unknown is f max. I'm going to say that's the positive direction, so it keeps it nice. So resolving horizontally, I've got f max minus, and the only other thing is this, that's horizontal, and that is x is equal to 0. And therefore, I can quite clearly say that f max must equal 7mg over 6 root 3. Okay? And all we're left to do now is to resolve vertically, and I'm trying to find y. Y is upwards, so I'm going to say upwards is positive. So I've got y is equal to, y minus 2mg minus mg equals 0. So y minus 2mg minus mg is equal to 0, and you've got basically y is equal to 3mg, and then finally you've got f max is equal to mu r, and therefore mu is equal to 7mg over root 3, all divided by 3mg. Divide by mg, or should I say top and bottom, and help me out. Oh, and the 6, yep, thank you. 6 root 3. And then the 3 comes to that, so you end up with basically 7 over 18 root 3 is what mu is equal to. Okay? Right. So working that out, because we need to work that one out and do the 3 sig fig, because G was involved in there at some stage. What do we get? Hopefully between 0 and 1, otherwise we're in real problems. 0.0225. 0.225 is what mu would work out to be there. So it's the same technique again. I'll go back through it. Look, you take moments about this point here because you've got the y and the f max gets rid of it, and you know this, know that, and you're just trying to find that. Then you resolve horizontally and resolve vertically. Okay, and Bob's your uncle. Mu equals f max divided by r. Rob? Right, I'll just make sure everyone knows that. If that's a contact, the force it provides, the reactional force, will always be normal to it. Always be right angles to it. Always. That's why this reactional force here, whatever that's stabbing into it, is still going to be a normal reaction to the contact surface. Okay? Over the page, there's your exercise. I hope that was of some use. Yeah. Raquel hasn't said much. Have you noticed, Connie? I hope I pressed shift, and I hope I did record this, otherwise we're in real problems, because I'm not doing that again. I don't know. Yeah. Bye.